Hello and welcome back to my MegaWang 2000 Turbo Edition hardware updates. People have asked me how I've managed to extract these graphics for Afterburner, or to find these graphics for Afterburner. I could have gone to somewhere like Sprite as resource, but they don't contain all of the graphics. I actually updated the MAME source code, specifically the Sega 16 sp.cpp source file here, which is the Sega Outrun board, but also Afterburner and Afterburner 2 board sprite drawing routine. I added a little bit of extra code, and this code looks at the palette data and the sprite data that is going through the emulated sprite draw, and it notices that if there is a unique sprite identifier, so this saved index here incorporates the address of the sprite inside the sprite data ROM, memory rather, and it also incorporates the palette index as well. And for Thunderblade, I added the ability to note a changed palette as well. So if the code was updating the palette, then it would also force a resave. But it just basically saves the raw RGB data from the palette data, from the sprite data, plus the palette bank as the emulator would have drawn it, but it just basically dumps it to a great big large binary file. So if I run Afterburner in this kind of like instrumented debug version of MAME, and I just let it run for a few frames and then quit, that's already captured some sprite data into that very large t.raw file. Let's look at this t.raw file in the hex editor so you can get a feel for what it looks like. There we go. It's just a whole great big bunch of RGB data. I'm using bright purple, which is RGB 255,0,255, as a transparency color, by the way. So once I have this very large t.raw dump file, I can use ImageMagick and the convert tool, which is included in ImageMagick. I can set the size to 512 by 256. I can give it the raw 8-bit RGB input and then tell it to output PNG files, and it automatically, which is fantastic, isn't it? It automatically cuts those up into individual PNG files, and it puts them into the directory that I told it to. Now, each sprite at the moment is 512 by 256. That's basically the largest sprite size that the hardware, or I chose, that the hardware can output when it's running in MAME. That's basically the largest width and the largest height that a hardware sprite can be, unscaled. I then tweaked my image conversion tool to shift all of the sprites to the top left and to reduce the size. So now we've cropped out, well, let's just refresh the directory view here. If I press F5, there we go. The thumbnail view wasn't quite caught up with all of the changes. So now all of those sprites have had their bounding boxes minimized, so that we can see now that we have nice individual sprites for the player's aircraft, rotated sky, there's a cloud. What's interesting to note is that actually the Afterburner arcade hardware has several different mapping sizes for the sprites. They've already done kind of like almost like MIP mapping but for scaled sprites, which is kind of sensible, I suppose. It helps to reduce pixel artifacting when you're shrinking down very large sprites. But there are some duplicates there, so I also tweaked the image conversion utility to spot duplicate sprite files, and now it's finished removing all of the duplicates. So now it went from, what was it, 185 plus 190 almost to 172 individual sprite frames. So even in that short intro sequence, there are, or the game displayed, a unique 172 sprites plus the rotated horizon sprites. It's interesting to note actually that the horizon that rotates is actually just pre-rotated sprites, which are displayed behind everything else. The hardware doesn't actually use like a Mode 7 layer for the for the horizon. Anyway, so once I have those sprites, then I can incorporate those sprites into the demo code for the Afterburner demo in using my MegaWang 2000 Turbo Edition hardware. I also added some debug code to this hacked version of MAME to save out PCM music data as an XM music file format. So to do this, I had to intercept where sample data was played using the PCM hardware, and also the note events for note off, note release, volume events, and pitch change events. So say, for example, with Daytona uses the Model 2 hardware, but it uses quite an advanced version of the Sega PCM hardware. So if I go to the sound test menu in Daytona and then choose the background music and then play this one, there we go, we've got some lovely music, which is the game advertisement music. We'll let that play for a bit so it can capture enough note events. Fantastic piece of music this. I mean, I used to really enjoy this in the arcade. Gosh, 30 years ago now, my word. Another piece of music, let's choose this one. This is the music that plays, I think, when you're being asked to select a race course or something, is it? It's a long time ago. Anyway, so once exiting out of the machine, the code then starts and it identifies where all of the samples start and end in memory from what was played in the music. And it also identifies the channels that are used and saves out all of the note events, the pitch events, the volume events. The code also saves out, so it saves out the raw sample data of samples that were just used. Let's see if I can find the command line to play that. So there we go, I'm using ffmpeg utilities ffplay, and that just plays, so the code saves out all of the samples that were played in the music or in the game, and it just saves them all out as a great big long raw file, which you can play back, and it's signed 8-bit audio as well. You can change the frequency that it plays it back at. Let's change that to 44.1 kilohertz. There we go. So that gives me the raw sample data, which is, you know, useful in itself if you want to identify sound effects and music instruments and stuff like that. But what's more useful, perhaps, is actually it saves out an XM music file format as well, which includes all of the note events and everything. So let's use Milky Tracker. Milky Tracker is one of the trackers that can handle 32-channel XM files. And there we go. This is the captured music now saved as an XM file format. Now, I can import XM files and convert the samples and the music events into something which can be played on the MegaWang audio hardware. That's what I used previously when I was converting Amiga mod files. So Amiga mod files and XM files and everything else, there's a sound driver source code that I kind of like co-opted to then optimize and save out for 4-channel MegaWang audio. So I was thinking I can use this hook, or these hooks, into saving XM file data and sample data into Afterburner. So Afterburner uses an earlier version of the PCM hardware, plus also a YM variant synthesis chip. So if I use the diagnostic menu to play the title tune, the great thing about these arcade titles is that usually they have like these diagnostic menus which lets you play music and stuff like that, all the sound effects. So let's quit that, and then again the save XM source code comes along and saves out all of the samples and the music events. Note it's only got 16 channels rather than 32 or 64 channels. So we'll load that into Milky Tracker and we'll kick it off. So it sounds roughly sensible, right? But there's some audio channels missing. So what's going on here? Why does the music not quite sound correct, and why does it have some missing audio channels? Well, if we go back to the Sega X board, which is the Outrun board, and we trace through from the Sega Afterburner 2 driver, and we trace back through, and then we get down to Sega X board state, X board base machine config there. So if we go into here, which sets up the base X board machine config, Afterburner 2 has a couple of little hardware tweaks in MAME for its emulation, but basically it uses the X board state, basically the same as Outrun almost. I mean, there were some hardware tweaks. There's some subtle differences between Outrun and Afterburner 2, for example, in terms of hardware, but basically we have the PCM hardware, which is what the save XM code was hooking into, right? So, say for example, the save XM code has hooks for sample data sizes and saving, and also note saving. So, the multi PCM driver, which was used for Daytona, has the hooks into the save XM code to save the note events, and also the Sega PCM driver as well has the same kind of like hooks for set note on, set note off, I think it was release and volume, right? Those are the important events. But the multi-PCM hardware and the Sega PCM hardware have different register usage, so that's why we've got two different drivers in MAME. So the save XM code has to have this common way of trying to identify, and so what it does is that it hooks into each driver source code level and identifies the events that way, because the register usage is entirely different. But the problem is that the save XM code is not saving out all of the music channels, right? As we heard. And why is that? Well, if we go back to the X board machine configuration, we can see why. It's because we've got a YM2151 sound chip there. So if I change the code to disconnect the YM2151 device from the output speakers, so I've commented out the route from the YM2151 chip to the output speakers. Okay, so now we're just left with the PCM device, which has speaker access. And if I go to the sound test menu and play the music, here we go. So you'll notice now that the music is also missing those channels that were missing from the saved XM music file. So this tells us conclusively that the YM2151 device is really important for supplying some of the music channels that are used in Afterburner. Unfortunately, the YM2151 device is different to the PCM device. So the PCM, it basically has, it's a sampled audio player, right? We have digital samples that goes through to the audio hardware. So yeah, so there's a clear difference there. So basically the YM2151 device is a synthesis device. It doesn't have samples as such that can get easily saved out into the XM music file. The YM2151 device calculates the audio that it plays on the fly, based on, depending on precisely which version of the YM device that it's using, it can synthesize different waveforms based on various different combinations of effects and waveforms and complexity and stuff like that. So the more complex chips have more complex waveform arrangements and filters and stuff like that. So that's where I am at the moment with saving out the music data from Afterburner Arcade, is that I need to figure out a way of identifying a good enough set of sample data that I can synthesize, which is a close enough match to the YM2151 synthesis as the arcade hardware plays it, and then convert that into like PCM samples that then I can save out as looping PCM sample chunks into the XM music file format. And also I need to identify the note on events and the pitch events and stuff like that too, and also save out those into the XM music file. So what I'm thinking is that the YM2151 device can probably have another bank of channels in addition to the PCM side of things. So it'll probably expand from 16 channels to 32 channels or something like that on the final output for the XM music file format. But yeah, so there's this thing here there's this code here which is update internal, which is part of the generic YM FM synthesis chip, which generates the samples on the fly, you see. But these samples, they have all of this complexity in terms of connected voice generation blocks and filters and all sorts of stuff like that. So I need to figure out all of that and then just connect that all together. So there we go. I think I'll leave this video there. Thank you very much for watching. If you like these kind of crazy electronics and retro software videos, then please do consider liking or subscribing to my channel, and I hope to catch you around next time.